You fill your tank to 200 bar at the dive center. It's a warm day, 35 degrees in the shop. You drive to the site, get kitted up, jump in. Before you've even taken a single breath, you check your gauge. 190 bar. You haven't used any air. So where did those 10 bar go? Or this one. Your student fills their tank to 200 bar and leaves it on the boat, in the sun. An hour later, the gauge reads higher than when they filled it. They think they got a free top-up. They didn't. Both situations have the same explanation, and once you understand it, you'll never look at a tank gauge the same way again. Welcome to Deep Dive Theory. Today, Charles's Law. In episodes 1 and 2, we covered how pressure affects gas, Boyle's Law. Today we add a second variable, temperature. And temperature changes everything, including how much air your tank actually contains. Jacques Charles was an 18th century French scientist and balloonist. In 1787, he discovered that gases expand when heated and contract when cooled, at a predictable, proportional rate. He never dived, but his law governs every scuba tank, every BCD, and every dry suit in the water. There are actually two laws we're looking at today. They're from the same family. Charles's law describes what happens to volume when temperature changes at constant pressure. Gay-Lussac's law describes what happens to pressure when temperature changes in a rigid container. In diving, we use both, and we group them together. The one rule that applies to both: temperature calculations must always be in Kelvin, not Celsius, not Fahrenheit, Kelvin. This is the single most common mistake at the instructor examination, and we're going to fix that today. First things first, Kelvin. Why do we use Kelvin and not Celsius? Because Celsius has an arbitrary 0 point. 0 degrees Celsius is the freezing point of water, a useful reference for daily life, but meaningless to a gas molecule. Kelvin starts at absolute 0, the point at which all molecular motion stops. That's the true 0 for gas behavior. The conversion is simple. Kelvin equals degrees Celsius plus 273. That's it. 20 degrees Celsius is 293 Kelvin. 0 degrees Celsius is 273 Kelvin. Minus 273 Celsius is 0 Kelvin. Absolute 0. K equals 200 degrees Celsius plus 273. Now the law itself. Charles's law. For flexible containers like your lungs, your BCD, or a balloon, V1 divided by T1 equals V2 divided by T2. Volume divided by temperature stays constant. If temperature goes up, volume goes up. If temperature drops, volume drops, proportionally, always in Kelvin. Practical example. A dry suit diver descends into cold water. The air trapped in the suit contracts even more as the temperature drops. The suit squeezes. The diver needs to add gas to maintain buoyancy and comfort. That's Charles's law. For rigid containers, like a steel or aluminum scuba tank, volume can't change. So when temperature changes, pressure changes instead. This is Gay-Lussac's law. P1 divided by T1 equals P2 divided by T2. Same structure, same logic, just pressure instead of volume. Temperature goes up, pressure goes up. Temperature drops, pressure drops. This is why your tank gauge reads differently in warm versus cold conditions, even with the same amount of air inside. Let's work through the scenario from the hook. Tank filled to 200 bar at 35 degrees Celsius in the dive shop. You get in the water, 20 degrees Celsius. What's the new pressure? Step 1. Convert to Kelvin. 35 degrees Celsius equals 308 Kelvin. 20 degrees Celsius equals 293 Kelvin. Step 2. Apply the formula. P1 divided by T1 equals P2 divided by T2. 200 divided by 308 equals P2 divided by 293. P2 equals 200 times 293 divided by 308. P2 approximate about 190 bar. 190 bar. 10 bar disappeared. Not because any air escaped, but because the temperature dropped and the pressure followed. The amount of air in the tank is identical. The gauge just reads lower. Now flip it. Same tank left in the sun after the dive. Temperature rises from 20 degrees to 40 degrees. The gauge goes up. Your student thinks they got extra air. They didn't. The air expanded under heat and the pressure increased. The quantity of air is unchanged. This is also why tank valves have burst discs, a safety feature that releases pressure if a tank overheats. The practical rule: always fill tanks in a cool, shaded environment, and always let a freshly filled tank cool before reading the final pressure. A hot fill reads high. When it cools, the real pressure is lower. Teaching Corner. Charles's Law is one of those topics where the concept is simple, but the calculation trips people up. Almost always because of Kelvin. Let's fix that permanently. Clarify Kelvin before anything else. Before you show a single formula, write K equals degrees Celsius plus 273 on the board and make every candidate convert 3 temperatures: 0 degrees Celsius, 20 degrees Celsius, 35 degrees Celsius. Takes 90 seconds. After that, Kelvin becomes automatic and the formula makes sense. Skip this step and you'll spend the rest of the session correcting Celsius errors. Thermometer analogy. Tell your students. Imagine a gas as a group of molecules bouncing around a room. The hotter it gets, the faster they bounce, and the harder they push on the walls. In a flexible room, balloon, BCD, lungs, the walls move outward, volume increases. In a rigid room, steel tank, the walls can't move, so the pressure on them increases instead. Same law, 2 different containers, 2 different outcomes. The shade, always wait to read. This is the single most practical application of Charles's Law for dive operators. Brief your IDC candidates on it as a dive center management point, not just a physics point. Fill tanks in shade or air-conditioned spaces, never in direct sunlight, and wait at least 10 minutes after filling before reading the final pressure. A tank filled in the sun at 40 degrees Celsius and then cooled to 20 degrees Celsius will read roughly 13 bar lower. That's not a leak. That's Charles's Law. One IE question. Pause if you want to work it out first. A scuba tank is filled to 200 bars at a temperature of 20 degrees Celsius. The diver enters the water where the temperature is 5 degrees Celsius. What is the new pressure in the tank? Convert first. 20 degrees Celsius equals 293 Kelvin. 5 degrees Celsius equals 278 Kelvin. Now apply Gay-Lussac's law. P2 equals P1 times T2 divided by T1. So 200 times 278 divided by 293, approximately 190 bars. 10 bars lower. No air lost, just cooler. Three things to take away from today. 1. Temperature and gas behavior are directly linked. Higher temperature equals higher pressure or volume. Lower temperature equals lower pressure or volume. 2. Always use Kelvin in gas law calculations. K equals d degrees Celsius plus 273. No exceptions. This is the IE killer. 3. Fill tanks in shade. Wait before reading the final pressure. Charles's Law in action. Every fill, every day. Next week, Episode 4, Dalton's Law. What happens when you mix gases? Why does nitrogen narcosis happen at depth? And why does the partial pressure of oxygen matter more than you think? Subscribe, drop your questions in the comments, and I'll see you in the next one.